Swayam Prabha. Digital India. Educated India.
Then it is as good as R load. If you say that the inductance is negligibly small, that even before switching, it is just giving away its energy, it doesn't have, that means it is as good as R load. In R load, you don't have to have the feedback diode, but most of our circuits will contain at least some minimum inductance. Because even the copper wires, thick copper wires have some inductance, just can't help it. So there is nothing like a pure resistive load except for maybe a few that you can mention as example for pure resistive load is your incandescent lamps. Many of them are purely resistive, hardly any inductance. If you look at our heater, what we have at home during winter, those things are, or immersion rods, most of them are having negligible inductance. Those are the typical examples of pure resistances. There is nothing like pure inductance. That's why the question I asked in the quiz is hypothetical. There is nothing like pure inductance. Any copper wire will also have a resistance. It is hypothetical, clearly. Okay? So if it is pure inductance, I'm going to have essentially L di by dt equal to V dc. Right? This is how it is going to be. So the current would have increased further and further until here. Maybe. Right? And during negative, if I assume that I'm going to have the same negative value here, it would have probably given back all the energy until here. So the diodes will, always the current will be positive. I am assuming pure inductance. Then in all probability, always the current would have been positive, provided I started off with a positive half cycle. If I had started off with a negative half cycle, always the current will be negative. Right? Hypothetical. Yes. Completely hypothetical. You get my point? So it's not an inverter anymore. Voltage is alternating. The current is not alternating.
And in this, if we started like not exactly from the middle of the cycle. So it will oscillate again.
You mean to say that if it is starting from here? Yes, it must have increased until here and then it must have, yes. It would have been something similar but with maybe same frequency as the supply voltage. What he is asking is, if rather than assuming that I am starting from the beginning 0, if I had started with pi by 2, so what will happen? So if I do like this, maybe the current would have gone like this, then it would have come down like this, again increased, decreased and so on. These things are interesting questions to handle using PSIM. Maybe you guys can try these things. It is really worth looking at those things if you, just want to check how the whole thing functions. Right? You're talking about even here? When the current is, No, at pi by 2, I have started the firing of 1 and 1 dash. See, you can imagine that still my frequency is actually from 0 to pi and pi to 2 pi, no doubt. 0 to pi, we are supposed to fire 1 and 1 dash. But it so happens that my computer or microprocessor or whatever, it is starting at this point. Arbitrarily, it has started from pi by 2. So, the current has increased until I had 1 and 1 dash fired, right? And it is pure inductance. So until then the current would have increased continuously. After that, I have fired 2 and 2 dash. So 1 and 1 dash will cease to conduct. I will remove the pulses from 1 and 1 dash and give it to 2 and 2 dash. In an inverter, never ever will we fire the two devices in the same leg. Never ever. If we try to do that, then this will be a dead shot. It will be called shoot-through condition. Shoot-through is deadly. So We cannot have pulses going to 1 as well as 2 dash. Similarly, 2 as well as 1 dash. I cannot have pulses going simultaneously. So the moment I fire 2 and 2 dash, 1 and 1 dash anyway have stopped conducting. Now the inductance will take over. So inductance is trying to feed back the energy through the diodes. When it is feeding back the energy through the diodes, we said that this positive is connected here and this negative is connected here. So the voltage of the load has completely gone inverted. That's the reason why we are seeing a negative voltage. Right? And once the current reaches, like if it reaches 0, then obviously I will not have these two diodes conducting. Rather, these two devices, the other two devices will start conducting, 2 and 2 dash. So in this particular case, I had to show as though 1 and 1 dash conduct here. And I'm going to have D2 and D2 dash conducting here. Right? And after that, 2 and 2 dash will conduct for this duration. And so on. When I have both voltage and current as positive, the power is flowing from DC side to AC side. When I have maybe one of them as positive and one of them as negative, the power is flowing the other way round, from the load into the battery. You get my point? And if I am having both of them to be negative during this duration, I will have the battery supplying the power to the load. And when I have one of them positive, the other one voltage negative, then I'm going to have again the power going, in the reverse direction. That is how it will be. So you have to see that, if both of them are actually in the same polarity, then the power is actually getting converted into AC. Otherwise, it's as though the load is feeding back to the mains, the battery. So the power direction can change.
Like protection of diodes.
Huh.
Like when we use diode in series.
Huh.
Like you told, we have to use like 2 resistors in parallel with the diodes.
Huh.
But like this protection work can also be done with the help of one resistor only. Like if you know the leakage currents of the 2 diodes, and if you make the equation, so by fixing one of the voltages, if I want like on one of the diodes the voltage should be this, I can always do the resistance.
No, you mean to say that, just a second, protection of, rather series connection of diodes. So you have one diode here, one more diode here, and their leakage currents are different. Their leakage currents are different, and they have to block a voltage. This is plus and this is minus. So they are blocking a large voltage. And normally we put something like this. 2 resistances we put in parallel. So you mean to say that only one resistance will do the job. That is, in this normally what we write is that if I say this is VD1 and this is VD2 and this is the total current I should rather show it the other way around, because leakage, it is the opposite direction. So this is the I leakage, total. So I'm going to have essentially VD1 divided by R1 plus whatever is the I leakage of 1, right, equal to VD2 divided by R2 plus what is I leakage of 2, together will be I leakage as such, right? So if you are saying that, let us use only one resistance such that these two are equated. That's what you are trying to say, right? See, only thing is, it depends upon whether you want to have even minor discrepancy between VD1 and VD2. I would like you guys to do this exercise. You say that maybe both of them have to block voltage of 10 kilovolts, right? And each of them is maybe rated for 6 kilovolts. Each is rated for 6 kilovolts. If I don't mind having a discrepancy of 1 kilovolts between the two blocking voltages, that is one case. And if I mind actually having any discrepancy at all, so for both cases you try to calculate and see which case has a higher copper loss. Definitely there will be copper losses. Please check how the copper losses will be. If I want exactly 5 kilovolts division among both the diodes, that is one case. The other cases, maybe one can have 5.5, the other one can have 4.5. You also take one of the examples from Rashid and see leakage current difference. Maybe one has, a few milliamperes, maybe 20 milliamperes, the other one has 30 milliamperes or something. There are at least 3 such solved examples given in the diode chapter of Rashid. So I feel that if you choose only one resistance, the copper losses could be much more. Maybe you try to calculate. Please try to calculate and check it up. I feel that it may be much more, but this is the standard practice that's very commonly used in HVDC systems and so on. Because in HVDC transmission, we normally use 84 to 100 series SCRs. One device will correspond to about 84 to 100 series SCRs. That's how it is. Yes, guys. Have you read already from the book? No? Yeah, but I told you that just don't take Bhuvaneshwari for granted, right? You should look at something else. Told you that. See, SCR characteristics is very, very similar to diode characteristics, except that by giving a gate pulse only, it is going to start conducting. But beyond a particular forward voltage, it will break down, break over, forward break over voltage. So if you try to apply beyond this value, let us say it is rated for 10 kilovolts, 7 kilovolts. So maybe that is 7 kilovolts. If you try to go beyond that, it will be a destructive breakdown. It will not be able to come back to normalcy. So you are going to see that this is the forward breakover voltage, and similarly I will have a reverse breakdown voltage, right? So I would be seeing that the device will break down in a destructive manner if I try to apply beyond that whatever is the rated voltage of that particular device. So in the reverse direction, if I draw, literally the current would be very, very small, leakage current, and then suddenly once you cross this, it has to increase quite a bit in the reverse direction. So that is like a destructive breakdown. And in the forward direction, even before the breakover voltage, if I actually try to apply a gate pulse, the moment the gate pulse comes, there will be a very, very short negative resistance kind of region which is transient, which you will not be able to operate the device continuously in that region. And after that, you would see that it is really following something like a diode's characteristics. Forward, regular resistance, whatever is the forward resistance multiplied by the current will be the voltage, that kind of characteristic. So this is going to be I and this is going to be V. So this is VFBO, VRBD. And if I give the gate bias with the higher intensity, right? So this is with the higher intensity. If I have only a lower intensity, then it will take more amount of gate current. Only if I have more gate current, at that point, it is going to probably start conducting. So if I look at actually the voltage that I have applied, whatever is the voltage applied, when it is very, very minimal, I will require a large amount of gate drive. If the voltage is somewhat higher, then I require only a lower amount of gate drive for the device to latch into conduction. To latch into conduction, it will require only less amount of gate drive. So this is going to be the different types of, but ultimately they all coincide. The moment it starts and latches into conduction, the characteristics are the same. But when I am applying a very, very small value of voltage, at that point, I might require a little bit more of the gate drive to latch the device into conduction. So actually these characteristics are not so much of importance for us, especially in power electronics, because most of the times we talk about 230 volts or 440 volts, compared to which the forward drop or anything is very, very small. And thyristors generally take a little longer to get into conduction and turn off also. Both takes longer. Because of that, 20 millisecond is still pretty small duration. It's not a very long duration. But if you are talking about something like MOSFET or IGBT, then yes, we have to worry about even the small duration from where it is rising from 0 to 5 volts or 3 volts or 4 volts. But in thyristor, we don't have to worry so much.
And like at the point of forward breakover,
Huh.
the characteristic will be the same.
Yeah, it will go all the way, and once it breaks down again, the resistance is going to be small. But it is gone, that's it. It may not respond to turning off at all. It is as good as you have short-circuited the device. I think it will lose control. To be honest, I have never seen a thyristor break down so easily. Normally MTBF, mean time between failure for thyristor, they say is infinity, literally. Mean time between failures for SCRs, thyristors, very difficult to break them, like induction motors. They'll not break down so easily. You have to really manhandle them. Then they'll break down. Otherwise, generally SCRs are very rugged, extremely rugged. And we had a freewheeling diode here. This was a freewheeling diode, and this was the load, whatever be the load. Freewheeling diode will not be there unless there is an RL load. There has to be an inductance, otherwise why would I have a freewheeling diode? Right? So this is the kind of circuit that we discussed. So I gave some frequency of turning on, turning off. I gave some minimum on time for the device, and then I asked you to design L and C. I think that's what I had asked you to do. This is main thyristor, this is the auxiliary thyristor, this is L, this let me call it as D1, and this is C. And we said that initial charging we are assuming, maybe through a resistance or whatever. This is the initial charging. I want to charge the capacitor beforehand so that it is ready for the commutation process. This is what we had given. So you know LC oscillation. Generally, pi root LC is the half cycle time. Right? This will be the half cycle time for LC oscillation. Right? This plays a very, very vital role in this, because once you turn on your M, the moment you turn on M, we said that this is going around like this. The current will go around like this, right? And we are assuming lossless devices. If it is lossless, I'm going to have plus and minus in the opposite sense in the capacitor. So if you actually look at the oscillation, I'm going to have the voltage going like this, right? Whereas my current, if I try to look at it, it will be somewhat like this. This is how the current will be. Right? LC oscillation current will be like this. So I should say this is voltage across capacitor, whereas this is current through the capacitor, assuming lossless devices. So this timing is corresponding to pi root LC, because this is half cycle time. So if the capacitance has to reverse its voltage, only then it is ready for commutating the main thyristor when I am firing the auxiliary SCR. So when you are going to fire the auxiliary thyristor, if the main thyristor has to go off, I should have plus here and minus here. And that plus minus would happen only if LC oscillation at least takes place until the half cycle time. Right? Because it has started with maybe plus VDC and it will go until minus VDC. Right? So it has started from plus VDC and this will go until minus VDC. Right? So I should have the main device on at least for pi root LC duration. If the main device is not on for pi root LC duration, the current will not be, really going through the complete half cycle so that the capacitant reverses its charge. And only if the capacitant reverses its charge, I'm going to have that capacitance ready to commutate the thyristor when I am firing A. Right? So this pi root LC has to be the minimum time for which M should be on. Minimum time. Of course it can be on for longer. Nobody is preventing that. So if I say the chopper has, for example, 1 kilohertz frequency and I want it to be on at least for 10% of that 1 kilohertz frequency time, 10% will correspond to 1 kilohertz is 1 millisecond. So it has to be on at least for 100 microseconds. So I should say 1 millisecond is 100%. I am talking about 10%. 10% will be, right? I am going to have basically 100 microsecond. 1 millisecond corresponds to 1000 microsecond. I am taking 1000 microsecond is 100%. So 10 microsecond, 100 microsecond is going to be 10%. So at least for 10% of duration, if I have to have this on, that means my pi root LC minimum duty ratio or minimum on time I want to have is 100 microsecond, then pi root LC has to be 100 microsecond. Right? At least 100 microsecond. Maybe slightly less than 100 microsecond is even better, because I have to make sure that the reversal takes place within that time. So this is one condition. This pi root LC will give me an expression for root of LC together. But how do I segregate L and C? I can always assume some L and say C is the other one. That's fine. But is there any other condition? The second condition is the moment I turn on auxiliary thyristor. So capacitor has reversed its charge. Right? So capacitor voltage is reversed. That's what I mean. Capacitor voltage is reversed in pi root LC time. After that, the main SCR is still on for some more time as long as the load is being fed. Now maybe I want to turn off the supply to the load. So I need to fire, A is fired when M has to be turned off. Right? This is what we said. The moment you fire A, I am going to have basically, this is my main thyristor, this is my capacitor voltage, which was having plus here and minus here. Auxiliary thyristor has become a short circuit. The moment, so this is A. A has become a short circuit. When A is short circuited, I'm going to have plus here. Please note this plus is applied here and the minus is applied here. So obviously this thyristor is going to have a huge bout of reverse current trying to flow in the opposite direction. But that large current cannot flow because the device will not allow that kind of a current, so it is going to be quenched. So the load current what you have is flowing in the forward direction.